Hello, my name is John Deck. I'm with the University of California at Berkeley in Biocode LLC. I'm going to talk today just really quickly about the Genomic Observatory's metadata and metadata architecture behind GEOME. And just a bit of background about GEOME. If you see the logo in the lower left-hand corner of the screen here, the Maria Biocode project logo, that was a project that began in 2006. And it was an all-taxon biotic inventory of a single tropical island where we had researchers from over 25 different institutions all working together, collecting data in a single database. And importantly, all of the researchers wanted to provision data back to their home institutions. So it was very important for the design of the system to be able to think about data integration between the project database, which was the Biocode database, and collection management systems that people were using. So we started thinking very early about data integration, metadata standards, and data validation for the project. And we came up with a system for people using spreadsheets, because field biologists love to use spreadsheets, and it's still the most common way of entering data. But the issues is that we wanted to provide data validation and data integration and use spreadsheets. How can you use spreadsheets and get data in that format and make it computable and make it work with other systems? So when we think about GEOME functions, the main functions first is to provide instant feedback on sample data contained in spreadsheets. We want to comply with global metadata standards, use persistent identifiers to aid in linking to external sources, and enabling users to manage data in distinct project spaces. The relevant bits of the technical architecture, currently it's in a Postgres database that is a relational database, but also NoSQL. Uses JSON to describe both the GEOME network and project-specific configurations, and we'll talk about that a little bit more later. It has transaction recording, enables rollbacks to any point in time for each project. It's built on a RESTful framework, and it runs on servers hosted by iDigBio, which is a project funded by the National Science Foundation in the US. So to talk about the user workflow when they interact with GEOME, the first thing a user does is they create a project. In a project, they choose particular classes and metadata fields and validation rules for their own project. And they choose from a list of data attributes that are community standard data attributes, such as Darwin core and minimum information about any type of sequence, which is the Genomic Standards Consortium standard. From there, users can generate spreadsheet templates, and this is where they enter data. So at that point, the user can be offline. They enter data into their spreadsheet. They could load data into GEOME, and GEOME gives them feedback about their metadata. Does it comply with the set of rules that they set out from the beginning? In addition, the user can take specimen and event photos associated with their specimen data. They can create FASTA files, so if they're doing barcoding, maybe they have barcodes contained in a FASTA file, or FASTQ files for next generation sequence data as well can be linked there. So we have GEOME as this, where it says load data, that's the core bit of GEOME that does the validation. There's other features that, such as a query interface and an R package that sits on top of GEOME. There's functions for working with tissues and working with 96-well plates, as well as optional linking to external projects. And we'll get into the external project linking on the next slide. So as far as metadata classes and modules, it begins with, at the highest level, events, collecting events. And samples are derived from collecting events. And you can take photos of samples or events. From here, users can optionally submit to the Global Biodiversity Information Facility their metadata. They can also take tissue subsamples or subsample data, which can be tissues, and link the tissues to the barcoding module. Users can then submit to a downstream system such as BOLD, optionally, If they have next-gen sequence data as FASTQ files, there's a submission tool to push data to the sequence read archive, which then has, once it gets there, there's a link to EBI. And we're working on currently environmental DNA handling. And what we've been talking about with some people in the community is using biome format files and amplicon sequence variants within those files to characterize everything that is in a particular eDNA sample. There would be a separate taxonomy classification service. This would likely be outside of GEOME, but the purpose of GEOME here is to contextualize the sample data and the event data and make sure that this data is linked to the ASV data. So when you create a biome file, all you have to worry about is loading in the appropriate ASVs and then linking in your sample metadata that's already in GEOME. This is an example of some collecting event metadata where you can see that there's a year collected, decimal latitude, longitude, locality description, collector lists, and then down here at the bottom you see child entities, which are samples. So in this case you can have multiple samples associated with a single collecting event. And if you click on a particular sample, you can see that there's child entities to the sample. And so here there's a child entity of a tissue that's associated with the sample. And if you click on the tissue, there's a child entity, for instance, of a FASTQ metadata file. And then from there, you can get all of this metadata for the FASTQ file. So as you can see, there's metadata attributes for each of these particular classes, and each of them have a unique identifier, which we call a bytecode commons identifier, the BCID, and a particular link. So you can link to distinct entities, the FASTQ metadata, tissue metadata, sample metadata, or the event metadata. And I think that's about all we have time for. If you want more information, you can go to the website, geom-db.org. You can also send me an email at jdeck@berkeley.edu. Thank you very much for your time.